Ora si registrerà la conferenza.
Bene, buongiorno a tutti, io sono Gianmarco Moroni e benvenuti anche oggi. Yes, the webinar will be in English, but the first part is in Italian as my introduction. Please wait a couple of minutes. Scusate, c'era un commento di un inglese che chiedeva se la lingua fosse stata in italiano o in inglese. Benvenuti, mi auguro che stiate tutti bene. Questo oggi è un grande evento ancora insieme ad Arturo Mediano, in collaborazione con un nostro fornitore inglese che si occupa appunto di realizzare degli scanner. Dopo ci sarà una piccola presentazione anche da parte di Cornell su questo tipo di strumentazione. Come dicevo prima, vi chiedo gentilmente di tenere muto il vostro microfono in autonomia, soprattutto magari nei primi minuti dove io non riesco ad intervenire. Andiamo velocemente, diamo inizio a questa giornata. Mi pare di averlo già detto prima, comunque l'evento è registrato, quindi poi a seguito, diciamo, quando vi invieremo la mail di ringraziamento, troverete anche il link della registrazione e potrete comodamente rivederlo. Per chi mi conosce e per chi non mi conosce, io sono Gianmarco Moroni, sono il titolare di Butterfly, sotto un po' di link per potervi connettere con me. Questa è l'agenda aggiornata al 6 maggio degli eventi che ci saranno appunto nei prossimi giorni. Giovedì ci sarà un evento sugli alimentatori bidirezionali e poi il 15 e il 6 maggio dovreste anche già aver ricevuto una mail, ci sono due eventi nuovi, uno sempre in collaborazione con il nostro primario partner Rodo Schwarz e Wurz, e il secondo invece si aggiunge anche la Engine Soft. Sono due eventi molto interessanti della durata di un paio d'ore. Probabilmente il 15 aprile lo devo regolare, non sarà dalle 16 alle 17, è un po' più lungo, comunque andrò a aggiornare la pagina del nostro sito. Butterfly è un'azienda di Bologna, siamo dietro l'aeroporto, fondata nel 2002, siamo totalmente autonomi per quanto riguarda la vendita, il marketing, l'amministrazione e la logistica. Per quanto riguarda l'attività presso i clienti, siamo operativi in tutto il territorio nazionale e grazie alla nostra piattaforma online possiamo vendere e spedire in tutta Europa. Siamo principalmente attivi nei settori di ricerca e sviluppo, produzione, enti di ricerca e didattica. Molti di voi oggi appartengono a un gruppo tipo università piuttosto che NFN, eccetera. Enti governativi, grosse aziende perché fanno manutenzioni di impianti industriali e grazie al sito siamo in grado anche di fornire parte della strumentazione anche all'utenza privata. Abbiamo due macro aree di applicazioni, una appunto legata alla parte di strumentazione di misura, applicazioni IMC e termografia, e l'altra legata alle protezioni ISD e alla saldatura manuale. Come dicevo, l'ho tenuta molto corta per dare poi più spazio possibile ad Arturo. Passo la parola a Cornell per una breve presentazione e dopodiché inizierà Arturo che stava riavviando il computer. Ora cerco Cornell. Hello Cornell, can you hear me?
Hello, good morning, Gianmarco. Hello,
Good.
ciao everybody.
Cornell, I'm going to pass you the speaker role, so you will have a pop-up on the computer and then you can share your screen.
Perfect, thank you.
Just let me know when you are, you should be already speaker. Yes, we can see your, we can see your screen. Yes,
okay,
perfect. So now I mute myself and I will join, yes, and I will regulate. Good job.
Thank you very much. Thank you. Thank you very much. And hello, everybody in Italy. It's lovely to be here today. So my name is Cornell Roberts and I am manager for YIC Technologies. And thank you for joining this webinар. If you have joined the previous webinars that we have conducted, whether it was the EMC troubleshooting or whether it was analyzing your scan then this webinar will take you a little bit further into the EMI journey. If you haven't attended the previous ones, don't worry, because we will cover all the fundamentals of the EMC challenges that you might face. So YC, what do we do is the solutions that we offer to you will give you a very way to look at your design. Our solutions rapidly identify your EMC challenges so that you can adjust at your lab or on your bench, and then you can retest. Means that you can take your product to the market much faster. So Butterfly is our partner in Italy. So if you have any queries with regards to any of our products or solutions or what you hear today, please get in touch with him and he will be able to answer all your queries if you might have. So now I'm going to introduce Professor Arturo to you. He is our technical advisor at YSC Technologies, and we work very closely with him. But he's also the founder of the HF Magic Lab at the University of Zaragoza. He will be leading today's presentation on the secrets of the EMC debugging. So if you have any questions or queries, or you would like him to go through something that you might want repeated, please pop it in the chat function, and then at the end of the webinar, we can go through that. So that's me. That's all I have to say today. So I'm going to hand you over now to Professor Arturo. Thank you very much.
Thank you very much, Cornel. Ciao, Arturo. Welcome.
Ciao, Gianmarco. Hello, Cornel. Good
Everything
morning.
is fine?
Fine, perfect.
Great. So you should have the speaker role at the moment, okay. And then you can go ahead with your presentation.
Okay, let me see if I have permission to share the screen. Perfect.
Yes.
So at this moment, you see my slide?
Exactly.
Excellent.
So before you start, sorry, just a reminder for our guests following the presentation. If you, we will have a question and answer at the end of the webinar. But in any case, if you like to write the question in the chat, please take a note, and I will then go through all of them. I mute myself. Have a good job, Arturo.
Okay, Gianmarco. Buongiorno, Italia. Many of my good friends are in Italy now, so I am very happy to be with you. And let's try to spend some time, I don't know, 1 hour and 15 minutes, something like that, talking about near-field debugging. And then we will have question and answers period. So let's start. By the way, the slides will be available for you if you want. Okay, so let's start with the first idea when debugging. Remember, you have 3 different elements. The first element you have is the culprit. What is the culprit? Is the circuit that intentionally or unintentionally is creating electromagnetic energy, and this energy will be affecting to the second element, that is the victim. So you need to identify 2 different points or 2 different elements in any EMI problem, is the culprit and the victim. How is the energy going from the culprit to the victim? You have 2 different possibilities. The first possibility is through the air. I mean, through a non-conductive path. The second possibility is that, for example, you have your system connected to some kind of cables that send the power supply. In the automotive business, you will be working with DC levels. In a home appliance, you will be working with AC 50, 60 hertz signals. So the idea is that the noise is going from the culprit to the victim conducted. So how can you sell a product in Europe, in the USA, in Asia? You need to pass a specific test that limit how much is the energy you can send to the victim and how much is the energy that you can conduct to the victim. And how the people solve this problem. Remember, many times the people do something like this. If the coupling is through the air, they can introduce shielding. This is one of the first solutions. The second solution from many people is to introduce filtering. So filtering is used when we have a conductive path and shielding when we have a non-conductive path. And with these kind of solutions, you are going to the coupling mechanism. You have another different solution that is to increase the immunity of your victim. How can you increase the immunity of your victim? For example, you can try to work slower, or perhaps you can try to work with high levels in digital electronics. As we go down in voltages, we are more sensitive. But where is the best solution for any EMI problem? The best solution is always to find the culprit and to kill the culprit. This is the thing you need to try to obtain a solution that is cheaper and usually more effective. So the first thing to do is to find where is the culprit. Let's go to the laboratory. And when being in the laboratory, you have results like this one. Look at this. In red color is the limit of regulations, something like this. Okay. And then we are measuring radiated emissions from 30 megahertz to 1 gigahertz, something like that, something that is typical. And you obtain something like this. What is the first thing you do? The first thing to do is to go to the markers option and you select the frequencies that you identify coming from your device under test. And you find that the distance between the peaks is 10 megahertz. And then you say, oh, my clock is 10 megahertz in frequency. So perhaps you can consider that they are harmonics of your switching activity. When you identify clearly where is the energy in this frequency spectrum, we call this a narrowband emission. This is related with the resolution bandwidth of your spectrum analyzer. In this spectrum analyzer, this is a Rodan-Schwarz spectrum analyzer, you can see here that the resolution bandwidth is 120 kilohertz. What happened in other possible results? You obtain something like this. And with a resolution bandwidth that is 120 kilohertz, what you identify is some kind of mountain that is over the limits. Look at this. It's very difficult to find what is below this mountain because the resolution bandwidth is very big. You can reduce the resolution bandwidth for troubleshooting, but not for EMC regulations. And then we go to the peak, or we go to with the marker to the emissions, and we find that this frequency is not related with my circuit. I am not switching at that frequency. I don't have oscillators at this frequency. So the typical causes of this emission are: one, ringing. You have some kind of circuit that is switching probably, and you have ringing in the waveforms. Or the second possibility, you have a parasitic oscillation. This is typically related with the layout of your circuit. So how we can find the origin of this energy? This is what we will try to do with the demos. So let's go to the laboratory. Let's go here to the laboratory. Let me show you my setup for today. Okay, let me remove this screen. Let's go here. Okay, this one. I have two cameras. And you can see in the first camera, in the top camera, you can see I have a system that is on top of the scanner. Forget about the scanner now. So I will be using the scanner in the second part of the demos. And I have several circuits. In the lower camera, you see a detail from the top view of the system. What happened here? Where is why I don't see this camera? So what happened here? The camera is not working. Select camera, this one. Okay, why is not my camera working? Okay, I don't know what is happening. So let's try to switch to close. I have some risk starting the camera to block the computer, but I will try this. Let me try this. Okay, let me try select camera, a new camera. Let's try select camera, this one. Now, I hope these kind of operations are dangerous. Okay, so now it's working. I have too many things connected to my computer. So you can see here 4 different PCBs. The first PCB is the power supply. This is a DC-DC converter that is creating 12 volts for the other electronic circuits. I have here a microcontroller board. It's an Arduino for the demos, is a good option. And I have here an RFID reader. This is for tags, for cards or for radio frequency identification systems, and it's working at 13.56 megahertz. The communication between the Arduino the microcontroller and the RFID card is using an SPI bus, and I have a display where I have the communication through some kind of I2C communication standard. Okay, so let's switch on the circuit, and you can see that the display is on, and now the system is waiting for a tag. Okay, so the system is waiting for a tag. When I put the tag on top of the reader, I detect every time I go with the tag on top of the reader, I change the mark. So this is the system, and consider that this is part of your product, and these different PC boards will be introduced inside of some kind of enclosure, metallic or plastic or something like that. Okay, so how is the emission from this product? So we are going to the lab, obviously with the system inside of the enclosure, and in my lab, I will be using this antenna. Okay, let me show you with the camera. Okay, this is a dipole, and I am going to connect the output of the antenna. The output of this antenna is voltage. So remember that measuring voltage, I can use an spectral analyzer, an EMI receiver, or an oscilloscope. I will be connecting the antenna to my RTO scope, channel number 1. Okay, so this, what I am looking at the screen is voltage. Let me show you the screen. This is the time domain signal from my antenna. Nothing special. You see this in the screen, you see that this is something like noise. Let me switch off my product. I switch off the product. The noise is reduced. I switch on the product again, and the noise increased. Because there is no important information in the time domain view, I go to the FFT. Let me do something like from DC up to 300 megahertz, and let's put a resolution bandwidth of 100 kilohertz. And let's start with the FFT of channel number 1. So you can see here the solution. Let me switch off my product. This is what I have in the environment. Okay? You can see the FM radio stations and some specific frequencies. Some of them disappear and appear randomly, no? As the circuits around my area receive this energy. The antenna receives this energy. Let me switch on. When I switch on, you can see this mountain around the FM band. So something is happening from my circuit. Consider that you are failing in radiated emissions because the peak that we are around the FM band is over the limits. Okay, so this is related with my first slide. Remember this slide here. No? You go to the lab and you have some interest in some specific frequency. So let's go to the to understand the problem. The problem is that with the antenna, you are measuring electric field. Why we are measuring electric field? Because typically these antennas are antennas with rods. I am not measuring magnetic field. Magnetic field is usually measured with loops. Why is not necessary to measure magnetic field? It's not necessary because in the far field, when we are far from the circuit, the ratio between the electric and the magnetic field, the wave impedance, is related with the impedance of the transmission, with the media where the signal is being propagated. In this case is the air, that is 377 ohms. And where is the signal I am receiving? The signal I am receiving is electric field. And this electric field with the antenna factor is converted to voltage. So what you really obtain from the antenna is voltage. This is what you see in the screen of your instrument. And this voltage is related with the electric field you are measuring. And the manufacturer of the antenna will give you the antenna factor. It's the conversion from the voltage to the electric field. If you are interested in calculation of magnetic field, you only need to apply this equation. When we are over the limits, we go close to the circuit. So I go close to the circuit. This is what we call the near field. And in the near field, we find that around the device under test, we have energy stored around the components, around the circuits, around the traces, around the wires. And the frequencies that find some specific and good antenna are able to be radiated. Not all the signals that you find in the near field can be found in the far field. You only find in the far field the signals that are effectively radiated. So you need to have some kind of good antenna for that frequencies. But it's very interesting to analyze the circuit in the near field. Why? Because in the near field, you can try to find where is the origin of your signals. And if you find where is the origin of your signals, you will be able to kill the source. Remember that this is the most effective solution. So let's go to work in the near field. In the near field, we will be able to analyze magnetic fields, H fields. This is related with current. This is related really with the IDT. Or you will be able to evaluate or to measure electric field. This is a problem related with voltage, really with DVDT. Every time you switch, you will have problems. So how can you manufacture your own near field probe? What you can do is to take a piece of loop, a small loop, and then you short circuit the inner conductor and the shield of coax cable. If you make a big loop, you will be very sensitive, but you will not have a spatial resolution. Then you can switch to the smaller loop where you will not be very sensitive, but you will be able to locate exactly the origin of the emissions in some specific integrated circuit, in some specific component, in some specific trace. That is because we work with different probes in different sizes. The commercial probes, usually the magnetic commercial probes, are shielded. You will see that this is something like to extend the shield of the coax cable until you go to create this gap. Then the probe is shielded for electric field and is sensitive to magnetic fields. If you are interested in electric field, the idea is that you put outside of the inner of the shield a small length of the inner conductor. And this a small tip will be able to pick up electric field lines from the environment. It's insensitive to magnetic field lines. No? If you have a very small tip, you will have a very good spatial resolution. If you want to be more sensitive, you can increase the size of the tip with some kind of bowl or some kind of metal plate. This is what you will find in commercial probes. Let's try to do this in my circuits. In my circuits, I can try to test PC boards. We can try to test cables, looking for activity in common mode or in differential mode, or we can test the leakage that is coming from enclosures, slots, or apertures in your mechanical designs. Let's go to the laboratory and we switch to the cameras again. One camera, the second camera. And now, instead of using the antenna, we remove the antenna. Remember, we are looking for signals that are close to the FM band. Where is my near field probe? Let me see. Here. So I'm going to connect my near field probe with a coax cable again to my RDO oscilloscope in channel number 1. This is my probe. It's a small loop, nothing special. Okay. Remember, you can manufacture your own probe, but I don't like to spend many time manufacturing things that I will be using for serious activities. This is the screen of the scope. You can see that nothing is in the screen because the signal is far from any circuit. Obviously, you can identify some small energy in the area of the FM radio because the cable and the probe are working like antennas. You can reduce this energy sometimes with a ferrite in the coax cable. And then when we put the the probe close to the circuit, you can see here what I find. What I find here, I am on top of the RFID reader. You can see that it's a signal quasi-sinusoidal with a strong amplitude around 13.56 megahertz. Okay, obviously you see the second harmonic, and I have the noise I am looking for in my circuit, but it's not very important in this area. In this area, I have more signals related with the RFID system. Look at this. The magnetic field that I am creating in this loop with the current is perpendicular. So if you put the probe, if you rotate the probe 90 degrees, you will go with the measured signal to 0. You can find the point where the magnitude will be close to 0. When I go to the computer with the microcontroller, we can identify the peaks that are coming from the clocks in the Arduino board. When I go to the display, I find the activity in the display. If you go close to the cables, you can identify the activity from the I2C communications or from the SPI communications. You can find some specific peaks of your radiation are coming from these connections. And when I go to the DC-DC converter, I can find a strong broadband emission that is around 100 megahertz. So my general analysis gives me the possibility to think that problems at that specific frequency where I am failing in radiated emissions is basically the DC-DC converter. Okay, so let's go to continue the analysis. But instead of using a near-field probe, I will be using a near-field scanner. Let me see why the screen is not refreshed. What happened here? Let me try to disconnect this. Okay, let me try to connect again. Okay, I need a new computer, but I don't have time to select the new computer and to install the new computer. Okay, so this is the idea of the scanner. You have two different philosophies in the scanners. Is one probe and one automatic robot move the probe around the circuit with different heights, or the scanner that is flat where you put on top of the scanner your circuit. So the idea is that you connect below the surface of the scanner. You have more than 1,000 of probes that are switched automatically. So you have a quasi-real picture of the activity in your device, and we can go from 150 kilohertz to 8 gigahertz with this solution. This is a bug. This is 150 kilohertz to 8 gigahertz. Okay, and then with this solution, we can extend the precision. If we go to the other scanner, that is the scanner R, is the high resolution scanner. The resolution you have here in the EM scanner, the first scanner I will be using, is around 7.5 millimeters. So it's a very nice solution for general scans and to solve many problems. But with the high resolution scanner, we have the possibility to increase the resolution to 60 microns. The idea is that the same scanner is inside of one structure that is able to move the loops mechanically below the surface of the device under test. Okay, this is very interesting to scan, for example, very small circuits like integrated circuits or specific areas of your PCB if you have a high density populated PCB. Okay, the EM Prof is a one-arm robot. I will describe it before. So what can you put on top? You can put the UDTs, you can put PCBs, you can put, for example, enclosures, looking for some kind of leakage from apertures, from ventilations, or you can scan cables looking for common mode and differential mode activities in your elements, no? And what two different things you can do? The two different things you can do is the spectral and the spatial scan. In the spectral scan, we will be looking for frequencies. What frequencies are coming from my device? In the spatial scan, we will be trying to find where that frequencies are located in the circuit. Today, I will show you again the main behavior of this scanner, but additionally, I will show you how to do an interleaved scan. An interleaved scan is a very easy to do task that gives you a higher resolution picture of the activity in your PCB. So let's go to the lab. Remember, in my imaginary problem, I am looking for activity around 100 megahertz. So let me remove the screen of the RTO scope, and then let me show you the system. This is my scanner. This is the high resolution scanner for the second part of the demo if we have time. This is my spectrum analyzer. You need to connect the spectrum analyzer to the scanner, and both the scanner and the spectrum analyzer are connected to the computer. Okay, the system is powered from this power supply with a, let me show you, 15 volts voltage. Okay, so let's try to show you this screen, and in the lower camera you can see a detail of the circuit I am testing. Okay, let me show you the columns and the rows, and I am going to open the software. The software for the scanner is called EM Viewer. EM Viewer is starting now. Okay, so this is the screen of the scanner, of the software, sorry. Okay, and then the system is now detecting and connecting to a scanner and a spectrum analyzer. Connected to a scanner and a spectrum analyzer. So if we go here, we will see that the instrument, the software found that the spectrum analyzer is the Ronsor FSH. The scanner I am using is the EM scanner. Let me try this one because I have the two scanners connected to the system. Let me change the scanner because now was activated the high resolution scanner, and then this configuration is not necessary. Okay, what you do inside of the scanner is to create nodes. We have different nodes: spectral scans, spatial scans, spectral and spatial scan at the same time. We can combine with handheld probes. We can compare spatial or spectral scans very easily. No, let me try to do a spectral scan. For the spectral scan, you need to specify what frequency range you want. Not too much. Try to put here the necessary frequency range. For example, from 10 megahertz up to 300 megahertz. Why? Because I have a problem at around 100 megahertz. The resolution bandwidth. What resolution bandwidth you need to put here? It depends on your spectrum analyzer. If you take a very small resolution bandwidth, you will have very high resolution and frequency, but the sweep will be very slow. If you go to a high resolution bandwidth, remember, you will be able to find very quickly the emissions, but you will detect mountains. So let's just start with 120 kilohertz, like a compromise possibility. And look at this. In the control level, we are only in level 1, 7.5 millimeters, because this scanner is not the high resolution scanner where you can select up to 8 different resolution levels, down to 60 microns. I'm going to measure peaks. So for example, I will be measuring the two most important peaks in my scan, and I need to specify the spectral scan probes. I am going to select none at this moment, and let me load an overlay picture. This is not really necessary, but it's a very good idea, no? You can import pictures, or you can import Gerber files. For example, you can import the Gerber file related with the silk screen, where you can identify the name of the components, or additionally, you can create files, Gerber files, where you can combine the top or the bottom traces, something like that, to follow where the signal is going. No, let me try this one. Is the silk screen with the I don't remember. Let me remove if I selected the bottom or the top or the top traces. Let me try again. Now this one is the silk screen with the top layer in the PCB, and then I need to put this in the same position like my PC board. My board is basically here. You can see that the first corner is P6, and I go to column X. I go to column X here. So in Gerber files, you have 100% scale, 1-to-1 scale, so it's not necessary to resize the circuit. We apply and we accept, and now we are ready to. Oh, sorry, I forgot when I have loaded the overlay. I need to specify some cells. Look at this. When I click here, the color switch to green. That means that this cell is selected for scanning. No, so for the spectral scan, it's not necessary to scan the full area below the PCB. I am going to select several random cells, and then I am ready to make a signal sweep. No? The first thing to do is to set up the spectrum analyzer. Now we are scanning. The scan is really fast, and when the scan is finished, then the system is detecting peaks. This is what I found below my device under test. Look at this, from 10 megahertz up to 300 megahertz, you can see several peaks at 32, at 64. This is another frequency that is 191. You can see the harmonics related with the two clocks that you can find in any Arduino board. This will be related in your system with the clocks you have in the microcontroller system. And additionally, you have these narrowband emissions that are related with the communications activity with the communication buses I am using. Remember, SPI and I2C. No? Additionally, I detect below my Arduino board this big mountain. So one possibility is that this mountain was created in this Arduino. But remember from my previous scanner with the handheld probe that in this area I found this energy, but if you go to a scan below the DC-DC converter, this energy is bigger. So the energy really is created in the DC-DC converter and is going to the Arduino board through the cables, through the power supply cables. This is what is really dangerous, no? Now, once you have the spectral scan done, you can create a spatial scan inside of this system, no? So you can put here any frequency, or you can select some of the frequencies we have identified with peaks. For example, 32 megahertz and resolution bandwidth 120 kilohertz. Now, it's important to select for this analysis the full number of cells we have below the device under test, because I am interested in finding where this signal is located. And then we'll run the test. Remember, what I am interested now is to find where is the path of the 32 megahertz first harmonic clock. Okay, so this is the results. So we have a really nice picture in colors. You can change the level of the scale, so we can go to find exactly where is the point with more activity. In this area is where you have the clock for one of the microcontrollers in the Arduino board, and I have here another clock. Both of them are 32 kilohertz, and we can go here. If you combine the silk screen with the traces, bottom or top traces, you can identify how is the current going through your PCB. You can see this in 3D. It's very useful to find where you have some specific area, or you can try to apply fixes. I don't know, a decoupling capacitor. You can change the firmware to see how it's affected the behavior of the circuit. A lot of things can be done in both the spectral and spatial scans. No. Additionally, for the spectral scan, remember I did this spectrum. We can repeat the spectrum with my product off. So I switch off the product and I repeat the spectral scan. Okay, let me repeat the spectral scan. One pop, it's finished. It's not necessary to measure the peaks at this moment, but he will do. Okay, so this is the device under test off. This is with the device under test on. Okay, we can go to the same scale. For example, in this scale, I have, let's go to the scale view. I am going in vertical from -3 to 20, -3 to 20. Okay, and let's go here to measure. This is -3 to 20. So let's go here to go in the same scale from -3 to 20. Oh no, this is bigger than 20, so 35, for example. And let's go again to the device under test off, and from we put from -3 to 35. Okay, so we can compare. No, this is the device under test on. This is the device under test off. Okay, so obviously the FM band I am finding when the system is off. Remember, I am not measuring in a shielded chamber or in a shielded tent, something like that. The emissions from the FM band is below the mountain of the energy I am creating with my system. So I can create some kind of, for example, a spectral comparison. When you select the spectral comparison inside of this window, you can introduce, let me try this. You can introduce here the results of your spectral. Let me reduce this one and reduce this one. And we can go here to the spectral, and we can put the reference view is what is the, for example, with the system off. And in the test view, we put the results with the system on. So this is the results with the device under test on. This is the reference view, the system off, and the comparison view will remove one from the other. So this is really the difference between the device under test on and the device under test off. It's in some way is the possibility to remove the ambient noise. This is not a perfect solution because I am not working with phase in my signals, but it's a very effective way to find some specific problems in the way in debugging. Okay. Let me show you something special in the spatial scan. If I go to the RFID reader, so now I go to the project option. Let's go to the spatial node, exactly, and let me try to scan the system at one specific frequency. For example, 13.5. No, let me try it first. This one. Let me create another. Delete this node. And let me create another spectral node that is going from 10 to 50 megahertz, not higher frequencies. I am not going to measure peaks. And now, instead of analyzing the microcontroller board, I am going to import a picture that is a picture for the RFID reader. Okay, so this is a picture you can take with your phone, for example. And we can go to put the picture in the good area. This is from AE to, let me see, AL. And we go down to this. So this is the picture of my RFID reader. If we go with the camera, let's try to go with the camera. Let me show you the antenna we have here. I hope you will be able to appreciate it. Okay, so this is my RFID card. So you can see that I have several capacitors for the resonance with the coil. And the coil is created with this kind of a square shape. I have 1, 2, 3, and 4 turns around one square shape loop. Okay, so the idea is that this chip that is working with the RFID protocol is introducing here a 13.56 megahertz quasi-sinusoidal signal for transmitting or for receiving while doing the communication. So how is the magnetic field around this RFID card? This is very interesting to debug RFID systems. If, for example, you can evaluate the influence of some specific plastic or metal close to the reader, no? So this is what I am going to do here. I will introduce you with the Interleaved scan. That is a very useful tool, no? So let's go to the scan. I didn't activate it probes, so I go to the settings again, and I put a picture, but I don't select it the cells below the device under test. Now I have selected all the cells below the device under test, and I start to sweep from 10 megahertz to 50 megahertz. Obviously, this is 13.56 megahertz, so I will be waiting for a first harmonic at that frequency, and probably second and third harmonic of this signal. Additionally, I can find here some noise coming from the digital communications coming to the circuit. So here you can see that I have here the 30.56 megahertz. Let me reduce the frequency range. Okay, let me go from 10 to 20 megahertz, and let me try a resolution bandwidth of 30 kilohertz. So we have a narrowband analysis, so we can find the peak of the signal. This is not very important, but it's good to show you the influence of the resolution bandwidth. Now it's sweeping some way slower because the resolution bandwidth is going to 1/3 from 100 kilohertz to 30 kilohertz. Now let's try to find the 13.56 megahertz signal. Okay, perfect. Oh no, I found what happened. This was wrong for me, and I was considering that the resolution bandwidth was not big enough. Let me change again, and I will explain you what is happening. Let's go to 120 kilohertz again. And remember that if you want to test any circuit, you need to switch on the circuit. If the system is off, you will not measure anything. So this is what was happening. Let's try again the scan. Sorry for this unintended problem. Okay, so it's scanning now, and I hope to see now a very clear 13.56 megahertz peak. This is something that I say to my students. Every time you are going to simulate, every time you are going to measure something, think about what are you waiting for, no? So you can see here with my resolution bandwidth, this is the first harmonic. If you want more precision, spatial frequency resolution, you can reduce the resolution bandwidth, no? So now inside of this, I am going to, to create a spatial node that will be analyzing the system at 13.56 megahertz. It's the main frequency of my system. And let's go to the spatial probes. It's all the probes below the circuit. And let me accept. It's something like previously. Now I am scanning this board in the same way I scanned the microcontroller board. And then I will show you what is the Interleaved scan. Okay, so you can see here the result. Clearly, for the 13.56 megahertz, I can increase or decrease the transparency of the overlay with the mouse wheel, or I can unselect the overlay. You can see that this result looks like very nice. No, it's following the square loop of the of the antenna, of the RFID antenna, no? But let me repeat the experiment, but instead of using the normal scan, I'm going to select interleaved scan. And the software give me some advice about what I am going to do. So I start, and the software let me, one moment, you are going to do an interleaved scan. That means you are going to scan the board 2 times. The first time is with the board in this position. So we repeat the scan, like previously. When the first sweep is done, the software stop and say me, you need to move the probe 1 row in the scanner. So you move the PC board 1 row in the scanner, and then you repeat the scan. Perhaps I will have some problem because I didn't activate these cells. Oh, this is a mistake, but okay, but I found it. So you can see the difference, okay? The difference is that with the interleaved scan, you obtain a picture that is closer to the real behavior of the current in your circuit. No? For many applications, this is a good approach, obviously. But if you are interested in finding exactly where is, you can do this interleaved scan. The idea is that the different probes in the rows of the scanner are used more effectively if you make this movement. This is the base of the high-resolution scanner. The base of the high-resolution scanner is that the scanner, without you doing nothing, the scanner is who is moving very slowly the loops below the device under test to obtain a very high resolution. Okay. Well, consider, for example, that you are interested in emissions. No. For example, I am interested in finding where is the origin of the problem, and I'm going to scan the DC-DC converter. So we go to the, let me rotate the camera. I'm going to scan the DC-DC converter. So let's go again here, and let me create a spectral spatial scan. In the spectral spatial scan, you select again a frequency range from 10 to 300 megahertz, 120 kilohertz in bandwidth. I'm not going to measure peaks, and let me load the, in this case, the picture of the DC-DC converter, this one. Okay, so I can put the DC-DC converter in place exactly in the point where it is located. It's from this position to this position, and this position is 25. Something like this. And in this PC board, really, I have 2 DC-DC converters. The top converter is for 12 volts. The second converter is for 5 volts. I am not using the 5 volts converter. So I'm going to activate only the cells that are below, more or less, the first converter. So the analysis will be faster. No? Let's go here. You make a run. Now it's different to the previous scans. Now with the spectral spatial scan, any of the cells you have selected are scanned in the full frequency range. Remember that in my previous spatial scan analysis, I was scanning spatially for one specific frequency I selected. Now I am identifying only the area of interest. You can see here, this is the picture of the PCB. You can see in 3D. So you can see in the PCB exactly where the origin is created. Many times, like in this DC-DC converter, this mountain that is the origin of the emissions in the FM band, remember this is 112 megahertz, this is the origin of the mountains I was creating. Sometimes this is related with the layout of the converter, the packages of the devices you are using in the converter, and sometimes the origin of this problem is ringing, no? So if we identify that the 100 emission is in the top of the DC-DC converter, it's time to go to the scope. Again, let me make in my scope a preset, and let's go to use this passive probe. The passive probe I will be using here. Let's go to the camera. Let's go to the camera. Okay. And remember that for this kind of measurements, it's not good to use this pigtail. It's usually recommended to remove the top of the cap of the tip, and then I usually take a piece of wire. You can find this like an accessory in the back of your probes, but I usually take a piece of wire. You remove the plastic, something like this. You cut in this way. You take the probe, and then you can make several turns around the metallic connection to the shield of the coax cable in this way. Okay, so in this way, you have a very, very small, let me try to show you here. You can see here that I have a very small pigtail, and then you need to have some kind of a specific socket. Like in my PC board, you can see specific sockets that can be useful for measuring the switching activity of your DC-DC converter. So let me try to see here. Let me see, this is the signal, okay. I am measuring without the, no, this is not a net. Let me remember where is the net I need to measure. I don't remember where is this one. Okay, let me try this one. Okay, I hope I will see the ringing anyway. No, the ringing is not here. All right, the idea is, sorry, I don't remember where is the socket. Let me try to remember the socket. This one is, let me try to do it. Sorry, wait a moment, please. Let me try to find the socket that is here. Okay, I'm going to use the pigtail on because I have not a good socket for this. No, I don't find this. This is the idea. The idea is that when analyzing your near-field probe, your waveform, you will find some waveform with this kind of behavior. The idea of not using this pigtail is because this pigtail can create this ringing, and then you will not be sure if the ringing you are looking at is in the circuit really or is in the probe, no? But I don't remember where are the correct sockets, so sorry, I don't want to lose a lot of time. Then when you have the ringing in the waveform, you take the markers, and then you can go with the markers from peak to peak, and then you will find, like this one, is that in the oscilloscope, the distance between the two vertical cursors is around 9 nanoseconds, that is 108 megahertz. This ringing is the origin. Yes? Yes.
So there is a question just 1 minute ago, if it is possible. They ask if you can swap the PCB from bottom to top and repeat the measure to check the difference. I don't know if it makes any sense, but I just want to read this question because it was 1 minute ago.
Yes. I will do this.
Okay.
For example, the DC-DC converter, no? Yes. I suppose it's the DC-DC converter. I will do this in 1 second. No problem. Okay. So this is the ringing. That is the origin of the problem. So typically, we try to redesign the circuit with a new layout, new packages, or for example, introducing a small Ferrite bit or a small RC snubber to damp this ringing. Remember, when you have ringing, it's because you have inductance and you have capacitance, typically parasitic inductance and capacitance. Because you don't have losses, there is a underdamped solution. If you introduce resistance through ferrites or through the snubber, you will be able to damp this ringing. Okay, so let's try to repeat the scan, for example, with in the both sides of the PCB. No, let me try to do this at the end. Okay, at the end of the experiment, I will do the other scan without problem. And let me go with the last part of the test. Let me zoom here to focus. Okay, and consider, for example, that you are interested in the activity in this cable, no? So the idea is you do something similar. You go to the project menu, you create a spectral spatial scan, and you go from 20 to 200 megahertz. 200 megahertz, and I am interested in analyzing the activity in the cable. So I go to the overlay editor because I have a picture of my cable. So in this way, you will be able to, let me try to do this, from this to this, okay, this one, this way, okay, this way. And this goes to this. Let me try to go here. Okay, so it's not very difficult to inside. More or less, my picture is in the same position like my cable. Obviously, the picture was taken before the preparation of the experiment, but it's more or less in the same position. So I apply, and I check here, and I say I'm interested in this area. This is the cells I want to scan. Accept, and then I scan. Then I am going to analyze how is the activity in this cable. Oh, sorry, this one. Let me make a zoom. And we will try to minimize the possibility to introduce noise in this cable. Why? Because at 100 megahertz, remember, 100 megahertz is a signal with a 3 meters wavelength. The typical elements that will be able to radiate 100 megahertz are cables, because one antenna needs to be in a size comparable to the wavelength of the signal. So frequencies from 30 megahertz up to, I don't know, 400 megahertz typically are radiated by cables. To radiate 600 with PCBs or with slots in enclosures, you need to go typically to hundreds of megahertz, 600, 700, 800 megahertz. You can see here the idea of the cable. And in green color, you can see how is the activity that is going through the cable, basically in common mode, because the two wires are one close to the other. So you can be interested in trying to minimize this emission. One of the things you can do is to try a ferrite. But how is the effectiveness of the ferrite? So I'm going to use this ferrite. Let me open a PDF file with the data sheet of the ferrite I will be using in the demo. Okay, you can see here that is a burst ferrite that is working at 100 megahertz. And if we go to the traces, to the response, you can see here, let me increase the size of the graph, that burst explain that the frequency behavior of the ferrite, the impedance of the ferrite in this frequency range, and especially at 100 megahertz, is around 200 ohms. This is a resistive activity. Remember, in the low frequency range, ferrites are reactive elements. In the area where is the peak and higher frequencies, the ferrite is resistive. This is what is interesting for my application. So I am considering to use 200 ohms in series with the cable in common mode. So let's open my box and let's show you the ferrite. If you have been in some of my previous webinars, you have seen this kind of ferrites that are very useful. See?
In the meanwhile, yes, you are looking for your ferrites. There is an interesting question which says, yes, why you are not taking, a picture of the full setup instead of taking a picture of every single board and then attribute the coordinate.
No, you can make a full picture without problem. This is only to show the webinar by parts, no? So yeah, the idea of this presentation is with the first scan of the Arduino board, I am presenting the spatial and the spectral scans. Then we go to a RFID card to show you the interleaved way. And then we go to the DC-DC converter to show the ringing and the activity in the cable. But
so
obviously,
just to answer to Fabio, it is possible to take one single picture with all the setup.
yes.
Good.
Let's.
Thank you very much.
I will do this in a few moments without problem. Let's put the Ferrite in place. Try to avoid movement of the cables, and then we repeat the experiment, and then we will be able to compare. And I will do the two things. We will be able to scan the board in the other side, and we will try to do a full scan of the setup. So now I am testing the same system, but with the Ferrite in place. Remember, it's a Ferrite that is introducing impedance basically in this area. And to compare the two results, you need to use the same scale. Now the system is in auto scale behavior. So let's try to stop. Wait a moment. Up, this way. This way, correct. And now I am finishing. Look at this. The red color is coming from the left side. Remember that from the left side, I am connected to the power supply. So the noise is coming from this side here. No? So let's go to the spectral scan here, and let's try to compare. No, this solution, this is, let's go to the data description. This is, the first one is without the Ferrite, and this second measurement is with the Ferrite. It's important to document your measurements because sometimes you have a lot. And I go to the without Ferrite. Let's go to the scale option, and let me put the scale fixed. For example, from 20 to 26. 20 to 26. And the second with the Ferrite in the same scale, from 20 to 26. Okay, and this is the difference with and without the Ferrite. Perhaps if we move the scale in this area, we can identify better. Okay, you can see how the signal is not able to be propagated through the cable so efficiently like without the Ferrite. No, okay, this is something that is very useful to find the system. Okay, so let's try to do a very fast scan. For example, let's consider that we want a spectral spatial scan from, we are interested in 100 megahertz. So let's start in, let's say 80 megahertz. Let's stop in 125, is the area where, or 130. Let's go to a resolution boundary of 300 kilohertz to be faster. And let's scan the full PCB. But to scan the full PCB, let's try to put different pictures here. This is the DC-DC converter. This is the, oh no, I have not a picture of the full system. Okay, no problem. Let's try to see the picture in top, something like this. Okay, and to avoid a long time, because we have a fixed time for the demo, let's try to evaluate select known, and I am going to activate the following cells. Let's try to do it with this camera. I think it's better. Let's try to see, is the second row orange to the last one, and from the first column orange to the last one. Okay, so something like this. Something like this. This is my area of interest. Okay, accept. If you take a picture of the full system, you will be able to put an overlay, and then we scan. Let's try to do this very fast. The system is on, correct, and we are scanning with the Ferrite in place. No, remember I am scanning only the area of interest. In the meantime, while the system is scanning, let me show you the idea of the high resolution scanner. The high resolution scanner can be seen with this camera. Okay. Okay. You can see here the high resolution scanner. Okay. is connected to the computer. And the idea is that with this scanner, you can scan in the same way like we have done previously, but additionally, the scanner can be moved, can have movements that are able to go with the resolution to very, very low values. So let's go to the slides again, and let me present this scanner. No? So the idea is that when you are preparing the node settings, you will be able to identify up to 8 levels of scanning. Obviously, if you go down in the spatial resolution, time for the scan increased drastically. Remember that we are increasing, I don't remember exactly, something like, yes, it's here, 4,000 times the number of points from the regular scan. So we can go from 7.5 millimeters to 60 microns, more or less, resolution. Why is this important? This is very useful to see the pictures in a different view. For example, in a normal scan, you can identify where you have activity, like I have shown you previously. With level 3, you can follow exactly the path of the signal. This is very useful to analyze, for example, the activity in a 2 layers or a multi-layers board, because in a multi-layers board, the activity in the inner layers are usually shielded by the external layers. If some activity is not shielded, you will identify the activity outside, and this activity is coming from the changing layers of signals, from areas where you don't have copper, for example, ground, or from the edge of the PC board. That is one of the more aggressive emissions area of the PCB at frequencies over 600 megahertz or something like that. So in the high resolution mode, you will be able to see very easily how is the path of the signal, like you can see here, or you can go to this test here, where we can analyze in different modes, different frequencies, where is the activity in some specific integrated circuit. I'm not going to do this test now because in the webinar, we need time for this, but if you see up the picture of the camera, you can see here, I have a small microcontroller board that is running a software very easily. It's only blinking a LED, okay? And then this is the result if you do the scan in different levels. Let's try to show you here. And then you can see that if we go to the level 1 in the small microcontroller board, let me show you the camera again. Okay. Okay, this something like this. Okay, here. Okay, this small microcontroller board gives me the possibility to find that in the frequency I am scanning, this board creates a strong 95 megahertz signal. So you can see that in the first level, I detect that the noise is coming from the integrated circuit, but scanning at higher levels, we are able to identify the pins where the signal is created, no? It's especially for high resolution. You can see this is the full scan, and from my scan, I am able to see yet what is here, what is here, what is here. No, obviously the levels at this 100 megahertz are coming basically from the DC-DC converter. We can find additional noise. You go to this scale, you can locate exactly the cell in the full system where you have the energy that you are creating. This is very important, especially when you are trying to find this kind of emissions. Remember, if you are trying to find this kind of problems, let me try to go to the slide where we have the results from the laboratory, this one, okay? If you are failing in something like this, sometimes it's very difficult to identify where is the origin of some specific frequency. I don't know, for example, 113.56 megahertz. What is the origin of this signal if you are not working at this frequency? No? if you are able to do this kind of scans, you can identify exactly the original problem. This DC-DC converter is switching at 500 kilohertz. So the harmonics goes to 1 megahertz, 1.5 megahertz, 2 megahertz. You have the even and the odd harmonics of the converter. But 100, 200 megahertz, 300 megahertz are not energy coming from the harmonics of the 500 kilohertz. The harmonics of the 500 kilohertz at these frequency levels are very, very, very low. No? So typically this is coming from ringing in the switching activity, like you have seen, or remember, from parasitic oscillation. So you can take a cutter, and you can try to cut the traces and to connect through other paths to see if you can destroy the parasitic feedback that is creating the oscillation. The scan is finished, and you can see how in my analysis, considering the frequency I was interested from 80 megahertz to 130 megahertz, I have detected the problem is coming from the DC-DC converter. And remember, you can put a full picture of your PC board, including the enclosure, if you are interested in finding the leakage in some specific areas. And the last thing to do, like I have promised, is to scan. Let me try a spectral spatial scan from 10 to 200 megahertz, for example, with a 300 kilohertz resolution bandwidth. Let me scan the DC-DC converter. Okay, so we are going to scan the converter in two sizes. So this one is the F. This is located here. Okay, let me go to the camera. Here is F here, and this one. So it's to here, more or less this way. Apply, okay. Okay, unselect, and I'm going to select the top converter. I am not using the bottom. Okay, and now I am going to scan directly. Let me show you the camera. We scan now in this frequency range, and then I will try to rotate the PCB. It's very fast. This is the similar. Obviously, I don't have a picture of the bottom side prepared because I have not considering to do this test. No? And now I disconnect the board, and what I usually work with is with this kind of paste. This is something like blue tack. I don't know the name in Italy, but this is usually used for fixing papers or posters in the walls. So I can go here, and I can put this here. Somewhere I will be fixing with my hand. Okay, so we can repeat the test. You have a picture. Remember to analyze a circuit, like when you are measuring signals, you need to think this when you are preparing the PCB. Obviously, if you are designing a circuit and you don't prepare test points, it will be very difficult to introduce a current probe or a voltage probe. This is the same. If you want to test a system with scanning tools, you need to have some kind of strategy when designing the PC board, especially in the first prototypes, to avoid very high components. So it's impossible to go down to the surface of the scanner. No, if you have very different heights in your PCBs, one possibility is to scan with a one probe robotic arm robot. No, you can see here the new solution. Obviously, the picture is not related with my activity. This is top layer. This is bottom layer. The opposite. This is the bottom layer. This is the top layer. Okay. You can see the noise is coming from both sides. It's a 2 layers board without ground plane. So it's easy to find where is the origin. So it's time to finish. We have been 1 hour and 45 minutes, and 15 minutes, something like that. So I will be happy to answer any question. Gianmarco.
Yes, great. Yes, I'm here. Thank you very much. So the question which came before, you already answered. Quindi il webinar, ok, quindi ora potete magari lasciare delle domande nella chat oppure magari una volta parlare. So there is a question. Can we use the scanner to debug a PCB when it has component in both layers, top and bottom?
It's a good question. If you have very different heights in the component, it will be different. It will be difficult. It will be difficult. Okay, you will need the one probe robot. That is the solution that you can change the height. But remember that, for example, let me show you this PCB. It's very useful to explain the idea. Here I have this, the PCB, this one. And I show you with the camera. Okay. For example, this PCB has no components in the lower. Yeah, there is no components here, but you can see that I have this. How to say in Italian or in English this word? These plastic legs for the PCB that are not a problem to scan the board. Obviously, you have components that are 1 centimeter or 2 centimeters in height. It will be very difficult to have a very nice picture, no? But you, in any way, you will be able to pick up red colors, hot areas, no? But if you, in the bottom layer, you have SMD components, for example, with not very high height, there is no problem to scan the board in both layers. Obviously, you can see that in the top of this PCB, I have a battery, and it will be very difficult to scan with resolution this area because of the height of the battery. One of the things you can do is to remove the battery and to power the circuit outside with the battery side by side. This is one solution. I hope to give you a good answer. More questions?
Not at the moment. Not at the moment. So maybe we wait a couple of minutes.
Anyway, if someone has any question, you can send to me an email, Gianmarco, and I will be happy to answer.
Yeah, for sure, for sure. Sicuramente se avrete domande anche tra qualche giorno potete scrivermi e le giro ad Arturo e vi girerò le risposte. Okay, so far there are no. Okay. If the tested DC-DC board has long wires and the noise is generated by a small ripple voltage, what is the question? Okay, can you still find the source on a magnetic?
Sorry, I don't understand the question, Gianmarco.
Wait, get a second. The question is writing the question in different chat. So okay. So okay. Let me read again. If the tested DC-DC board has long wires and the noise is generated by a small ripple voltage, can you still find the source on a magnetic scanner?
Yeah, well, this is a good question. In my experience, 90% of the problem, always you have magnetic field. You have electric field and the opposite. Electric and magnetic fields are very well related. Usually you have magnetic field when you have currents and you have electric field when you have voltage. But always you have one field, you have the other. Why we use magnetic field probes? Basically, several reasons. One, electric field probes are more sensitive to the environment and are more sensitive to the user. When you are touching an electric field probe, you are affecting the measurement a lot more than if you are using a magnetic field probe. This is one reason. The second reason is that in EMI, 90% of the problems are related with currents, and especially how you control the path of current. So for example, if you have some DC-DC converter and you have some kind of ringing that you think that this is the problem, perhaps the problem is not really the voltage. Perhaps what you are doing is that the cables are being excited with this ripple, this is voltage, and then the noise you are introducing in this antenna, in these cables, is creating the emissions. With the emissions, you are creating electric and magnetic fields, but the origin of the problem is because of the current you are injecting in the cables. This is the main idea to use magnetic field probes. 90% of the problems probably are related with currents injected in wires or circulating through traces in PCBs. With a scanner, you cannot scan electric fields, only magnetic fields. More?
Yeah, there is a question, but is there any?
Sorry, Gianmarco. Let me add another comment. This is very important. This is very important and it's related with the previous question. Consider, for example, that you have a component, an ASIC or a microcontroller, and you see in radiated emissions something like this. And people say, this is my clock. So I am radiating because I have a clock. And then this is the clock. This is the clock. How is the frequency of this clock? F0. How is the voltage waveform? This one. This is all the people think when thinking in clocks. If you are D and I say you the word clock, you think about this. And this is what? This is voltage. But remember that it's very important how is the current associated to this clock. It's the current that goes through this trace and is returning through the ground plane. And how is the current? The current in digital circuits is something like this. Every time you switch from 0 to 1 and from 1 to 0, the current is a peak because you are injecting current in a capacitive load. So every time you have DVDT, you inject a pulse of current. How is the frequency of this signal? It's F0. So really, the problem of your emissions because of the clock is the voltage or is the current? Many times, the problem is the current. The current is what is creating voltage drops in the ground plane. The current is what you are injecting in cables. The current is what is going to adjacent traces. But not only this. Consider, for example, the power supply line. This integrated circuit is being powered by 3 volts. How is the voltage in this 3 volts signal? The voltage is this, is DC, 3 volts, DC. There is no DVDT. And how is the current? The current is this current, and it's doing something like this. Sorry, something like this. Look at this. When in a digital circuit with many technologies, every time you switch, you have a peak of current that is positive. So if this peak is what you are doing from off to on, this peak is related with this peak in the power supply. And this peak that is negative in the clock signal is this peak in the power supply. So how is the frequency of the current in the power supply? The frequency of the current is 2F0, is 2 times the frequency of your clock. And this is a very common problem in digital circuits. What you will be radiating looks like the clock, but you are not radiating the clock signal. You are radiating the activity that the clock signal is creating in your power supply system. Why? Because you have the cables that are connected to the power supply, and these cables are the good antennas. So remember, thinking is always in current. In EMI, you need to think in current. Think in voltage, but don't forget current. Okay, Gianmarco, next question.
Yeah, yes. So is it possible to further increase the resolution of the scanner by moving the DUT just half a cell instead of 1 cell?
No, because the scanner has an structure with cells in different orientations. And what you do when going from one row to the other is using the different orientations of the cells, of the loops.
All right.
I think it's okay.
Okay, so I try to read this question, but it's a little bit scattered on different messages. So is there any importance to distinguish common mode and differential mode with a spatial scanner? So how do you know if you need a common mode filter, ferrite clamp, or a differential mode filter?
Okay. For radiated emissions, like previously, I know that it's a common mode, always. Why? Obviously, with the scanner, I am measuring differential and common mode, both of them. But look at this. In the analysis, what I have in my camera, you can see, okay, for example, let's go to the camera. Let's go to this camera here. Okay, you can see that this cable has the two wires, one close to the other. So with the scanner, I am measuring differential mode and common mode. But the problem that is creating this problem, this cable, is common mode, basically common mode, because the magnetic field that is radiating this cable to the environment is minimum. The differential mode current in the red color wire is cancelled by the differential mode current in the other wire. It's different in this situation. You can see that these cables are separated. You have two cables that are separated. You have problem with differential loop and with the common mode current, both of them. This is different for conducted emissions problems. Instead of radiated emission problems, you have a problem with conducted emissions. Both currents can be important. And with the scanner, you will not be able to identify if this is common mode or this is differential mode. Perhaps one thing you can do is to scan with the two wires separated and then scan with the two wires, one close to the other, and to see how is the difference. If some frequencies disappear when the two wires are one close to the other, that signals that frequencies were differential mode. And because you are connecting the two wires one close to the other, they disappear in the scanner, okay? You can complement this kind of measurement with a current probe. If you have some kind of current probes, you can combine very efficiently the results from the scanner with the results with the current probe. So you open the current probe and you can measure the common mode, or you can measure how much is the differential mode. So you do this. Okay, let me go this. Okay, when you have the cable like this. Okay, if you take the current probe in this position, you will be measuring common mode current. And then if you do this, let me try to do this. Okay, something like this. You will be measuring differential mode current. Okay, and then you can complement with the scanner to see the frequency range for each of the measurements. More questions?
No, but of course, all attendees are thanking you for the very good answers.
Okay, thank you.
Okay, so at this point, if there are no other questions, because it's 12:03, so we are out of our timing. Arturo, again, I mean, I can stop thanking you for your great support in our activities. And I switch to Italian. Grazie mille a tutti, vi ricordo che il seminario è stato registrato, quindi tra domani e domani l'altro vi invierò appunto una mail di ringraziamento che conterrà il link per scaricare il webinar, e ovviamente se avrete nei prossimi giorni delle domande potete contattarci e ovviamente noi faremo il nostro lavoro. Perfetto, grazie Arturo, grazie Cornel, hello everybody, see you the next time, ci vediamo la prossima volta, grazie a tutti.
Bye bye.
Thank you very much. Bye bye. Bye.
Bye bye Marco, bye bye Cornel.
Bye bye, ciao Cornel, ciao
Thanks
Arturo.
a lot.
Bye,
Good
bye.
job, Arturo. Good job. Thank you.
Thank you. Bye bye. I hope to be able to visit Italy soon.
Well,
Yes,
we
me
are
too.
trying our best, Arturo, you know this. Me and Leo, we are really trying the best.
I need to take some pizza or something like that as soon as
For
possible.
Yes,
sure. We all
I'll
need
be
that.
there.
Bye bye.
Bye. Thank you very much.
Bye-bye.
Bye-bye. Bye-bye.
Bye-bye.